Okay. Good morning, everyone. I'm Alatz and I'm going to present the impact of hardware characterization errors in digital analog quantum computing and the calibration error resilient protocols that we have developed for these errors. Now, to do so, I'm going to first introduce what is digital analog quantum computing. Then I'm going to talk about the hardware error that we're going to find. I'm going to discuss the stability of digital analog, and then I'm going to present the error mitigation protocol that we have developed. To explain digital analog quantum computing, I'm going to first go over analog quantum computing, which is the implementation of a continuous evolution over our state. Now, usually this is a very natural quantum interaction of many spins, for example, and it has a lot of pros, like, for example, it's not really prone to have decoherence errors because it's not going to be evolved by the outside forces like the environment. Also, it's really resource efficient because analog quantum computing is usually designed to do a specific task. Like we want to simulate any kind of Hamiltonian. The one that we are going to be implementing is going to be just for that specific task. This comes to a price, which is this quantum computing is not very flexible. It's going to be for these specific problems. And also, we don't have a universal quantum computing. On the other hand, we have digital quantum computing, where we implement discrete evolutions using single qubit gates and 2 qubit gates. Now, here we have universality. We can basically do any kind of simulations, any kind of logical gates. It's very versatile. Most of the algorithms that have been designed are for this paradigm, like for example, source algorithm. But it comes to a price which is being more prone to have decoherence errors. And also, it's more resource consuming. But what happens if we combine both? If we combine both, we can get universality back again by implementing and entangling operations with single qubit gates. And also, we are going to have a more robust paradigm because we're implementing natural quantum systems in our quantum computation. And how do we do this? To explain how we work with digital analog, I'm going to go over a simple problem, which is simulating a set Ising-Hamiltonian during a time t. Now, imagine we have a Hamiltonian that we want to simulate, which is our problem Hamiltonian. It's a set Ising-Hamiltonian with some couplings, and then our source is going to also be a set Hamiltonian with different couplings. By implementing what we call a sandwiching structure, this is using single qubit rotations between the implementation of our source Hamiltonian, we can effectively change the signs of our couplings, and by doing this structure over a circuit, we get the following equation that we can solve for the different times. Now here, M is going to represent a matrix of the signs change. This is a matrix that is going to be composed by ones and minus ones, depending if the rotations that we are implementing in our block are changing the sign of our coupling. For a more general problem, like an arbitrary two-body Hamiltonian, we are going to be implementing the same sandwiching structure, but now our sandwich for a different coupling is going to be composed up to 9 different sandwiching structures with the different rotations that we are going to be implementing. The equation that we are going to get from this is going to be the same, but what the change we are having here is how we construct the signs matrix. Now, how do we construct this sign matrix is something that Mikkel has gone over in his paper, Digital Analog Quantum Computation with Arbitrary Two-Body Hamiltonians, but here we only are going to have in mind that it is a matrix that is going to represent the signs of the couplings. We are not going to go over the structure, and it's not going to be really something that we are going to discuss. Now, before I go and explain how we characterize the hardware error, I'm going to give a brief explanation of the notation that we are using. This is an example of a graph. Here we are representing a setup of 6 qubits with different couplings, the couplings being these lines. Now, some important notation that we need to remember here are the edges, which are going to be the couplings between these qubits. In this example, we have 7 edges. Now, the vertices represent the qubits. So a vertex is just like the 5th qubit, for example, and we have a total of 6. And now the degree of a graph is going to be the qubit that has the biggest amount of couplings. The number of those couplings is the degree of our graph. In this example, the qubit 3 has 4 couplings. We can see like 4 edges, and the degree of this graph is going to be 4. Now for our characterization, we are going to have 3 different Hamiltonians. The source Hamiltonian that is going to be represented by the graph S, our problem Hamiltonian that we want to simulate that is represented by the graph P, and the error Hamiltonian that is going to be represented by the graph D. In our digital analog paradigm, even though there's different sources of error, we're going to be studying the error that we have in our analog Hamiltonian. Now, when we implement any kind of coupling Hamiltonian entangling, usually experimentally, we are going to be expecting some kind of error that is going to be represented as an Ising Hamiltonian, arbitrary two-body Hamiltonian. To do so, we also are going to be bounding the maximum coupling that this Hamiltonian can have by delta, which will be called the hardware error. This is the maximum error that we can get for any kind of interaction. When we turn on this Hamiltonian, this analog Hamiltonian, the source is not going to be perfect. And this will be represented by having a different source Hamiltonian that is composed by the errorless Hamiltonian that we were supposed to have and the error one. And also, the couplings that the different qubits are going to experience are going to be different. Now, what this causes is that the Hamiltonian that we are going to simulate by implementing our circuit is not going to be the one that we expected. We're going to have a different Hamiltonian with different couplings. Now, what we want to know now is how different this Hamiltonian and the couplings are going to be. And to do so, we are going to rely on something fundamental, that is, the applied schedule is going to be the same one as if we were to have an errorless Hamiltonian. This means that we have done the design for a Hamiltonian that has no errors, and then we are applying this circuit to an error Hamiltonian. So all the different couplings are going to experience, for example, the problem Hamiltonian couplings, they're going to have this error, and the source Hamiltonian, they're going to have the delta error, but they are going to be the same structure, which is given by the matrix signs and the different times that we are implementing these blocks. Now, if we solve this equation, we are going to get how the coupling of the problem Hamiltonians are changing, which is given by H epsilon. Now, so far, we've only assumed that the errors are going to be in the couplings that we are taking into account. But something that happens usually when we have any kind of experiment is that we are going to experience unwanted interactions. Let's say you have 4 qubits and you want to have an interaction between the first and the second, 1, 3, 1, 4, but suddenly you have a 2, 3 unexpected coupling that you didn't want to. Now, if we take that into account, our error is going to be divided into 2 different errors. Now, this is the one that we have solved for all the couplings that we have taken into account, and this is the error that we are experiencing on all the ones that we didn't count for. What this means is that we have the matrix M alpha is going to be an extension. This means that, for example, even though I'm not accounting for these errors, if I apply single qubit gates, these errors can be affected by these rotations, so they can have their signs change. To bound this expression by the p-norm, we're going to take first the errors that the couplings that we were expecting, and then the ones that we didn't. Now, this is really direct bounding. For the second part, we bound thinking that these unwanted errors, the unexpected errors, are not going to be changed in any part of our circuit. So they are just accumulating the maximum error delta. On the other hand, the parts that we were expecting are going to be given by just what we have solved so far. Now, to bound the Hamiltonian error, or to see the difference between the one that we are applying the circuit to and the one that we are getting, we only need to check the error Hamiltonian after applying the different rotations. And by just bounding, we can see that this bound is given by the one norm of the vectorize of these couplings, which results in this bound. Now here we have a representation of all the values that we have taken account for that are going to be given by the delta error are the sum of all the different all the differences between the problem Hamiltonian and the simulating Hamiltonian, and then the part that we didn't account for are going to be the edges here. That means the total number of couplings that we didn't account for, multiplied by the total time that we are simulating this circuit and the maximum error. This means that all these couplings are just amounting at the maximum error that they can during the whole circuit. Now, to discuss the stability of digital analog, once that we know how these errors affect the Hamiltonians, we are going to rely on this definition of a stable simulation task. What this means overall is that the difference of the expected value of an observable for a density matrix that has been evolved with the Hamiltonian that we were expecting, the one that has no errors, with the median value of the observable of the Hamiltonian that we are really simulating, must be bounded by a function that only depends on the error parameter and not the dimension of the system, and in such a way that if this error tends to 0, so does the function. If we apply these expressions, don't mind the case, it's just something that slipped. If we apply these different evolutions to our density matrix, the system that we have, we are going to see that this expression is going to be bounded by the operator norm of that expression. And now we have two general approaches. First, it's going to be not implementing trotter. We are going to have a circuit that has the different blocks, and every block has its own evolution, and this yields that bound, which is not, it doesn't give us much information because we don't really know what the problem Hamiltonian that we have for each block is going to be. It's a really hard thing to solve, and also we cannot find a general bound for the times that we are playing these blocks, so we don't get really much information from this. Now if we trotterize, we get better bounds, we have for if the problem Hamiltonian and the problem Hamiltonian that has an error commute, we have this expression, but it's not going to be very useful because usually errors are going to be in directions that don't commute, so we cannot expect for these two Hamiltonians to commute. And then we have this expression if they don't commute. But if you remember the expression that we have for the Hamiltonian in this part, which is the sum of the differences between the, oh, by the way, this is the element-wise division. I didn't say so, sorry. This means that for the vectors, they are going to be, for the first element of the vector is going to be divided by the first element of this vector, and so on. Now, here we have a weak sense of the dimension of the system, because we are going to be doing a sum of all the parameters that we have in the vector. So we have a kind of a sense of n, so it doesn't fulfill the stability requirements. Now, to extract more information from this stability, what we are going to do is a small error approximation. Now, we can divide our evolution into two evolutions, which will be the ideal evolution of a source Hamiltonian that has no error, and then the evolution that is caused by the errors, by just having these analogical errors. Now we are going to assume that delta is small in the sense that it's much smaller than the smallest coupling that we have in our source. With this, we can approximate the evolution of our error evolution to a first order and simplify it just as the expression of the identity and the Hamiltonian that we are applying. By doing so, we can approximate this stability equation to the trace of the commutator of the error Hamiltonian and the observable. To do the analysis of this, we are going to be taking a really common observable, which is the measurements of populations. We are going to do it first to 1 qubit, then we are going to extend to measuring m qubits. Now, if we take, we are also going to be measuring the first qubit because we don't lose any generality and it's easier to just solve it this way. Now, if we change x by the Hamiltonian expression that we have, if we get back all the information, we have two different expressions in our stability. This is going to be the expression of all the errors that we are counting for, all these couplings that we have accounted for, and this is going to be the errors of the ones that we didn't. If you take notice, this being the commutator means that we are only going to have non-zero values if the qubit I is going to be the first qubit, because all the rest are going to commute. This expression is going to be bounded by this, which means that we have the maximum error value, which will be delta multiplied by the maximum value that we can find in the difference between the couplings of HP and the couplings of HS, multiplied by the total amount of couplings that we have, because we are going over all the couplings here. Now for the second part, we are going to have a similar strategy, but this time what we are going to be counting are all the couplings that we have not taken into account, which is given by a graph of D that doesn't contain all the couplings of S. Now, to analyze these results, the stability requirements are going to be the following. For the first part, we only need, this is the expression for m qubits, by the way, if we are going to be measuring m qubits. It's just having the maximum stability possible multiplied by m. Now, the stability requirements are going to be for the first part that no qubit is going to have a number of couplings that scales with n, and that the observable must be local. This means that the degree is not going to depend on n, and also m is not going to depend on n. In a more physical way, this translates as we have an n-dimensional system. We cannot expect to have the local requirements for stability if we are measuring an n amount of qubits, and we can also not expect locality if one of the qubits is going to be interacting with all the qubits. We need to have interaction that is going to be on a local part, not with all the qubits, and also not measure all the qubits or something that is proportional to. Now for the second part, we can see that we have the same requirements. We cannot expect errors with all the qubits because then we are losing locality, and we cannot be measuring all the qubits also. But we have also one more requirement, which would be finding a total simulation time that is not dependent of n. Now, bounding this time is going to be really hard. We don't have a bound for a general case, so just for a few cases. So what we are going to do here, our strategy to reach stability, is going to extend the source Hamiltonian. This means all the couplings that we are taking into account, such that we are going to have all the errors taken account for. This is some way of doing a dynamical decoupling, because if we take into account for when we are designing our circuit all the errors that we are going to be experiencing, we can design our circuit by solving the equation in such a way that these errors are going to be cancelled, because we are experiencing the change in the couplings, so they are going to cancel themselves. But this comes to a trade-off, which means that we are going to have a longer simulation time. This is an example to have an intuition on how we are losing evolution, how we are making it longer just to get more stability. Now, our decoupling strategy is going to be all the errors, all the problem Hamiltonians that we are not expecting, and all the source Hamiltonians that we don't have, which would be something as having a division by 0, calling them 0. This means the problem Hamiltonians that should not be expected are going to be 0 in the design of our circuit, instead of not taking them into account. And if we solve this for 3 qubits by minimizing the total time, we can get a total time of simulation that is the sum of the 2 first parameters. But if we totally remove this part of the circuit, this means that we are not going to take into account this part of the Hamiltonian because it's 0. We don't have any couplings in the source either. The minimum value is going to be by the maximum value of any of those parameters. And we can see that the simulation time for removing these couplings, the ones that they are not in the problem Hamiltonian, is going to be less or up to equal to having zeros. On a more intuitive way to understand this is that if we don't take into account these problem couplings, we are going to have more free parameters. If we need to have 4 different times, for this equation we only have 1 free parameter. For the other approach we have 2. So we have more liberty when it comes to minimizing this equation. So the conclusions to this work is that we have proven that digital analog under certain conditions is stable, and for certain problems, which means that we can extend digital analog to larger qubit systems, and instead of just small and medium qubit systems. We have also proposed a new design that mitigates these calibration errors and helps us ensuring that we have this stability, but this design is going to come to a cost, which means the increasement of the total circuit time. So thanks for your attention, and if you have any questions. Yes.
You said in some moment that you need your observable to be local.
Yes.
To fulfill this condition. What do you mean exactly?
The observable mean local means that, for example, in this case, the measurement of the populations is going to be on a part of the system and not covering the whole system dimension.
So you have to measure a small number of qubits.
It's not necessarily small. It can be large, but not as large as something that would be. If I go to make a drawing, because maybe it's easier to understand it, but imagine you have a system of n qubits. Now, if you measure something that is proportional to n, you are not going to have locality, because imagine you keep just escalating that dimension. Now, you can measure something that has an infinite dimension or is proportional to that. So you have to measure something like a local part of your system. So that's what a local,
for example, like classical, so like common algorithms such as Shor or Grover, so they fulfill this.
It's more about the. It depends on what you are going to measure afterwards. It's not the algorithm per se, but for example, measuring the results. If you want to measure your whole state, you have an n-dimension state. If you have to measure all of it, it's not going to fulfill locality.
That's the case in Shor and Grover and so on.
You measure one.
For example, in SOR, the locality could come depending on the precision that you need. So if you want a precision that scales with the number of qubits, then you cannot, but if you want a limited precision, then okay. For Grover, yeah.
Regarding the editing, because I remember the matrix of the class remaining ones is the L matrix of before.
Yes.
But then I don't understand why it's anything square anymore and what are the consequences of this regarding the solutions of the system, and also I am not understanding why you can just make count all of the couplings as non-existing, and how might that affect to all of the rest of the errors?
What do you mean by counting all the couplings?
So let's go to why it's not in square anymore, that matrix, and how...
Let's use an example for 3 qubits. I think the 4 times strategy to have to fulfill the condition that all the times must be positive. That is something that you need to have. This is one of the conditions, and I think we have this 3 parameter just to fulfill that condition when it comes to solving this optimization problem. But in reality, we are going to have 3 qubits, and we are going to be implementing 3 blocks.
That system has a unique solution every time, or does it?
Come again?
Can you get a unique solution for that kind of problem?
I don't know. Thing is, this example is something that I put into, it's not my example, it's Mikkel's example. So I'm not that familiar, my bad, not that familiar with if the solution is unique or not, but this is an optimization problem that has some constraints, and to fulfill those constraints, this is the solution. Now, if the solution is unique or not, I don't know, but this is a solution that has the constraints. It's the minimum circuit by total circuit time that we can get, and also all the times are positive.
Okay, because the solution of that problem is the times.
Yes.
And you have to have a solution that fulfills. So it's important at least to have a solution.
Yes.
Right? And then my question is because I am not understanding how I don't know if the N matrix has information of the system. And then the source thingy where you have your qubits. Then I don't understand how you can just remove a part of the system and not any consequences.
Because the parts you are removing is when imagine you want to have a simulation of one of your problem in Hamiltonian, and one of the couplings they are not going to be coupled in principle. Like from qubit one, yeah, physically you don't expect them to have any coupling, and the source you are going to implement, you don't expect it to have couplings either, right?
Okay.
So you have two ways of approaching this. Now, if there's no coupling, then I don't have to take it into account, it doesn't exist. Or I have zero coupling for both of them, and I'm going to have some kind of source coupling, but not in my problem. So this means that the solution is going to be zero for my problem, but I have a coupling in my source, some sort of coupling. And this sort, when you think that you might have some source of coupling, you are taking into account when you are designing your circuit that there's going to be something there. So you are going to be extending your circuit in a way that you are going to be, for example, implementing more blocks. To just take into account this, to make it zero, because you don't want to have any kind of coupling in your solution. I don't know if I make myself clear.
For me, it's confusing because you mentioned, you were talking about you mentioned that you implement a sort of Hamiltonian, that I thought that you were referring that the source Hamiltonian is the Hamiltonian of the system. So you don't implement, per se, a Hamiltonian, it's just the system.
Yes.
Then if another doubt that I have, it's just out of curiosity, how can coupling that it's not in the system appear? I don't know if maybe
Because, yes, that's the thing. You don't expect theoretically to appear, but then you are going to experience some experimental errors where you are going to, when you are designing this analog system. For example, let's say you have Rydberg atoms, right? And you want these Rydberg atoms to have some sort of, I don't know, whatever they have. But to do this system, you need to have 0 Kelvin. But you're not going to have 0 Kelvin, so the atoms are going to experience some kind of heat motion, and then this heat motion are going to change the position of the atoms, and thus changing the force that these atoms are going to experience from other atoms. But you didn't account for that. You didn't account for the atom motion. You don't know how. You can only expect certain values of the motion, but you don't know how. So you are going to do the operation as I think I have a perfect setting where I have 0 Kelvin, but then my error is going to give me the possibility of this movement. So that's how it is. You're supposed to not have that kind of interactions in your setting, but due to experimental errors, you're going to have them. There's our unwanted experimental.
Okay, I can see what you're doing. But still, I have doubts if for example, that's coupling that appear in the system. Of course, if you're implementing some kind of simulation and the problem is simpler than that, if you want it to be 0, but it's not 0. I mean, I guess that I am not understanding this because as I asking here, okay, but let's think that it's zero, and let's get rid of this topic. It's really there. Then my question is, isn't this detrimental for the entire process, not taking into account the
Yes.
and activity?
Yes, it is. Yes, yes, it is. And that detrimental can be seen here in the second part. Now, this only appears because you are not taking into account some of the interaction of the Hamiltonian. So what you are going to be experiencing is that the maximum error is going to be accumulating during this unwanted, during all the circuit for all these unwanted couplings. Now, that is what you are going to experience for not taking them into account.
Okay, so you include this thing into the bound of the vertical space.
Yes. All the stability, here the analysis is by not taking into account these unwanted Hamiltonians. They are not going to be part of what you did when you design the circuit. You're not going to take them into account, and the result is going to be that if you are incredibly unlucky, you're going to get this maximum error. It's going to be piling over all your circuit, and you're going to have the full circuit during the full circuit time this error. And we are losing stability because we are not able to bound the total circuit time. For the cases that we have, we can prove that it's stable, but it's not a trivial task to actually bound this time. Yes?
One thing you mentioned that sounded strange to me is that using dynamical decoupling is going to probably extend the protocol, right? The total time is going to be longer. So in my experience with dynamical decoupling, that's not the case. So can you just like every analog block subdividing, so creating more analog blocks of the same total length and applying the case in the middle to do the dynamical decoupling? So increase the number of blocks in the same time. I would say that should give you the same time originally, but with dynamical decoupling.
Now, maybe if you apply those strategies, I don't know, maybe you are going to get the same time as you are optimizing the circuit, but I don't really know. I cannot answer the question. So.
And I have two more evil questions.
Yes.
Okay, evil questions. First one. So yeah, I do like some heavy approximations. So for me, like, the main one is this Taylor expansion of the propagator, right? You are cutting it to first order.
Here.
Yeah. Do you have like numerical support that this approximation should hold?
No.
So that's a big step. And my other question is, so this work, like the purpose is to show that in an experiment, this is going to give you some robustness, right? Like the system is robust. But you are only considering errors in the coupling between the qubits. So is this justifiable? Because I imagine you have a lot more things that are probably even more important, like external noise, like errors in the gates. So these other things.
External noise can be also characterized by this this Hamiltonian. We can also the thing about
it could be, for example, if it's in the resonant frequency of the qubits, that you cannot consider that as a coupling between the qubits in your system, right?
Well,
so it's like this error Hamiltonian a good model for an experimental system to consider errors?
Well, I mean, for most of our errors, yes. Like, for example, in ion traps, you get, if you're applying the Z direction, when you're applying, you get unwanted XX crosstalk, for example. Now, if what you are going to do is experience that kind of motion, for example, if the motion is in the same direction as all the couplings and whatever. This is just going to be something like.
But for example, in a system like ions, in which many gates are with laser, which is quite difficult to stabilize and control,
Yes.
then you are going to your single qubit gates are going to be quite. So you are going to have your single qubit gates and things like that.
Yes.
Model this.
No, but we are only taking into account the errors that we have in our in the part of the entanglement Hamiltonian. The errors for the single qubit gates are another part of the digital analog. It's not something that we are studying here.
Yes. Have you considered, I mean, here in your error calculation about two-body errors, have you considered errors of the body interactions or?
Not yet. Maybe we will consider them highly unlikely. Like most of the operations that you need to do, you can get universality by just applying the two-body Hamiltonians, and I don't think there's much to gain by applying free the entanglement between three qubits, and it's kind of a pain mathematically speaking. So
Yeah, I mean, I know that it's a problem that it's a bit sometimes. It gets harder to when you have many body. But I mean, they are much more operation.
any other questions?
Have more evil questions. Your evil questions were very good, by the way. Can you explain more or less what's the motivation of studying stability? Because you presented the definition from this paper from Franco Chirac and so on. So what's the motivation of extending this to digital analog?
I would say that the motivation would be ensuring that we can extend digital analog to bigger systems. If all the simulations or what we want to apply to digital analog paradigms, if they don't fulfill stability requirements, I don't see much use of extending the dimensions. So this is like the first step that we need to make to ensure that we can keep the qubit numbers growing.
So I would say because Chirac gave a talk in quantum matter about this paper, and he said that, okay, this is very interesting because people forget about analog simulations. They prove that analog simulation can be stable under those conditions. So it's good to have something that is universal and can be also seen as stable. So this is why I think this paper is very, very interesting.
I think we have a little bit of a problem with this. Is that we are losing universality because some specific Hamiltonians cannot be simulated being stable. For example, an all-to-all Hamiltonian is not going to fulfill the stability requirements, so we are reducing universality with these simulation tasks stability requirements.
Also, a comment that I got from someone in the conference is that, okay, if you have to apply some Adrian Barreras swap strategies that might scale with the number of qubits, then it's harder to prove stability in that situation at the first step. It's good. I have a general some comments. So, for example, in the slide 6, very careful because I think you got something that makes much sense. There, in the after times change, you have some vector equals some vectors times a matrix times another vector.
Yeah, I need to.
I would say that's very, very. I would keep the usual notation because the n should not be a matrix but like tension.
Yes.
So it's supposed to be.
What does it mean actually, the equation?
No, not the way. Go to the next slide. Yeah, it's this one, but written in another different way. We are always doing matrix time vector equal to.
The actual matrix would be all this. If you want to consider this as a vector, this would be the matrix.
Yes,
It's the actual matrix. But if you consider only one vector, which would be the element-wise division, then you can consider it as a matrix.
Be careful with that,
Yes.
those strange things.
I need to polish a little bit
Yes.
this presentation.
Okay, then one of the things you said is that the errors in the Hamiltonian come from external fluctuations or things, but we are mostly interested in calibration errors, because this is what Carlos said, that maybe your laser is fluctuating and at some point you measure something, but then it drifts to some other things, and that is not the environment, but it's something that,
Yes.
yeah, so the main focus of this is
Or like the example that I gave from the Ripper atoms
Yes.
with the atom motion. Yes.
the river atoms or superconducting circuits
Yes.
with IBM calibration that changes with
I
time.
forgot to mention the
Yeah.
errors that we can get from calibrating.
And also for the presentation, I think that many questions, specifically for Anna, comes from the lack of pictures. Because if you plot some pictures, then it's
Yes,
more easy.
yes.
You can easily see, like, okay, where these extra interactions go and why I can take out this
Yeah,
part
I
of the
think I'm
equation.
going to be putting more graphs
Yeah,
just to show
Yeah.
the examples.
Specifically in a presentation like this. Maybe not to bore people, I will stop here.
I have a question. In one of the first slides, you showed the definition of analog law. You put time-dependent Hamiltonian. So for me, that's quite strange, because if I assume that Hamiltonian is arbitrary, then that's the most general type of evolution, of unitary evolution. So that would be a digital computer, or that would be.
But once you know what your Hamiltonian is, you can only do certain specific tasks. I mean, yes, you can.
If it's an arbitrary Hamiltonian and it's independent, I mean,
Yes, I understand. Yes, you can. You can, yes, but the universality comes from being able to implement any kind of Hamiltonian, while the universality in digital quantum computation comes that I have a few kind of interactions, and then I can combine them to make new. From this Hamiltonian, by implementing, for example, annealing, there's if you have, let's say, a specific Hamiltonian, there's not much you can do. So you're going to have to get universality, you are going to need a set of a universal set of Hamiltonians. So what we mean with universality is by a finite set of operations, you can develop any kind of computation.
I think we can stop here.
Thank you.